Let's do this. All right, it is the time. February the 3rd. Let's get the daily challenge going. Hello, everyone. So this is today's LeetCode daily challenge. First, I take a look. Any new updates here? No, nothing updates. All right, let's do it. Linked list cycle. I might have heard of this before. A linked list cycle. Is it to detect a cycle in a linked list? Given the head of a linked list, determine if the linked list has a cycle. Yeah, it's a detecting cycle. There's a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, position is used to denote the index of the node that tail's next pointer is connected to. It's not passed as parameter. The node that tails next. Okay, so we have an index, but it's not given us, which is fine. Return true if there's a cycle in the. Otherwise, I think I've done this before, and I think I failed. Yeah, I definitely done this before. But oh man, I remember that time when I did it, and I was like, oh yeah, that's a great solution. And yeah, this is what LeetCode did to you. You did it a few months ago, and you're like, I got it. And then a few months later, nah, you forgot about it again. Okay, so basically, there are going to be two. There are going to be 2 pointers. I'm pretty sure there are 2 pointers. And one is going fast and the other is going slow. That's what I remember. But how is that working? It's like we start from the same and one always jump over. Is that what it is? One is always jump over and the other go one by one. Is that what it is? I think that is what it is. One always jump 2 at a time. 2 at a time. 2 at a time. So basically, we're talking about how many. I mean, if everything is linked from front to end, then one is going 1 at a time, the other going 2 at a time, 2 at a time, 2 at a time, 2 at a time. So they all meet, right? I mean, if there's no, how should I say? If there is no cycle, then the 2 shall never meet. If there is a cycle, then the 2 will meet one way or another. If they're even number, right? If they're even number or odd number, it doesn't really matter. Jump into it. Eventually it will. I mean, either go like 1, 2, go like this. 1, 2, 1, 2, 1, 2. So and anyway, it's just the whole point is if one goes fast and the other goes slow, then the fast one, if it ever meets, yeah, I think that is the solution. I'm not 100% sure, but going here. So if I go 2, will be here, 1 will be here, and then we go 2 will be here, 1 will be here. So they do meet. Okay, I haven't done this before. Let's hope that this solution is correct. That's what I think. We're gonna do copy today, today. If you've never done this before, this could be a medium, high medium problem. That's how I would describe it. But I vaguely remember how this is solved. Vaguely. Very, very vaguely. All right, let's take a look. How shall we do it? We're gonna have two nodes. We're gonna have n1 is head, n1 is n2 equals head. And while, do they not go together or do they go together? While true. So we don't have to handle this. But what if n2 is, I just have to check. If n1 dot next, well, while n1, if we hit n2 will hit first, right? So we can just say while n2 dot next and n2, yeah, just n2 dot next, because n2 dot next is good, then we can always go like that. So while n2, and n2 dot next, n1 equals n1 dot next, n2 equals n2 dot next dot next. If at any point n1 and n2 is the same, then we report that can we use, it didn't say if these things are, hold on. Can we make them the same number? I'm just curious. I think this one is true. I think we can just directly compare n1 and n2. Yeah, I can, if n1 equals n2, then return true, else we're gonna return false. All right, let's give this a shot. See if it works. I am not sure, man. I am very much not sure. This could be very wrong. Okay, they give me a true. That's good. 1, 2. 1, 2, and 0. This gives me a true, and then 1, and -1. I will just change it to -1. And this gives us a false. I guess we got it. Ha! Not 100% sure. Let's check it. Oh, we got it. That means I did remember it correctly. I did remember it correctly. Yeah, 80 milliseconds. Yeah, I bet the best solution is similar, huh? How could it be any different? Fast, slow. Yeah, it's exactly the same. Fast on next, fast on next, on next. Yeah, it's the same. It's the same. The same solution. It's the same solution. Well, because of this, it did maybe like one iteration less, so it's a little bit faster. That's how I think it is. But you have to write this, right? You have to write another piece of code. But yeah, this one I've done it before. Yeah, I've done it before. That said, we should still check. Every time, even if you've done it, you should just still go back. Let's see when I did it before. I did not do it before. Wait, what the heck? I didn't do it before? I thought I definitely did. I think I probably did some. Did I do this one? Linked list cycle 2? Oh, I did this one. I did this one, the cycle 2. Wait, what's the difference between the two? All right, that's interesting. Let's take a look at this later. But for this one, it's very straightforward. It's an easy question. A straightforward, easy question. Discussion. Let's check a hash table. We go to node one by one and record each node's reference in a hash table. If the current node is null, we have reached the end. of the list, and it must not be a cyclic. If current node reference is in the hash table, then return true. Okay, that is good. Floyd cycle. That's what it's called, the Floyd cycle. All right, this is called Floyd cycle. Okay, so I'm gonna write a little bit. I vaguely, how do you spell vague? Remembered that I had done a similar problem before. And the solution is the traditional, it's the official one, traditional one, the traditional two-pointer was the traditional two-pointer solution with a slow node and a fast node. The slow node goes one at a time, while the fast two at a time. If there is a cycle in the linked list, then the slow and the fast will meet each other somewhere during iteration. I checked the official solution, and this method is called Floyd Cycle. Floyd Cycle. When runtime, how much time did we get on this one? Like on 80 milliseconds. I think it's like about 10% ranking. I don't really care about this at this moment. All right, I just want to read. I just want to see if there's anything interesting. The hash method is fine. I don't really care about the hash method. Two runners, what happens when the track is actually a circle? Yeah, they'll meet each other. Slow and fast. One step at a time, move two steps at a time. No circle, then the fast will eventually reach the end. If there is a circle, the fast runner will meet the slow runner. Why? The fast runner is just one step ahead of the slow runner. In the next iteration, they both increment 1 and 2 steps, respectively, and meet each other. Well, I mean, every time they move, the fast will be incrementing one step further, and by the time it reaches, so yeah, they definitely will meet each other because the slow and fast as they're going, right? So the fast is always one step faster, right? One step faster. So if it ever circles back, and the slow one just goes slow. So every time it circles back, doesn't matter. The fast one will always be one step faster. So until the moment that when the faster one circles back and the slow one is in front of the fast one, then what we're talking about is just the fast one at each iteration is getting closer one step at a time towards the slow one. So they will eventually meet. So this is definitely going to happen. Runner's 2 or 3 steps behind the slow runner yet. Because next, it gives you a case. Yeah, this is fine. List has no cycle. When list has cycle, we break down the movement of the slow pointer into 2 steps, the non-cyclic part and the cyclic part. Enter the cycle. At this point, the fast one's already reached the cycle. And then both iteration equals none. Non-cyclic length. And both pointers are now in the cycle. So there are 2 runners running a cycle. The fast runner moves 2 steps, while the slow runner moves 1 step at a time. Takes, yes, most cyclic length k. And the speed difference is 1. So we conclude that number of iterations equals almost cyclic length k. The worst case complexity is n plus k, and which is O(n). It's n plus k because you have to take into consideration that you have to go into the circle. I mean, it's actually quite complicated, I think. I should analyze the runtime. But let's just treat it as O(n). It feels like O(n), so probably is O(n). Any people have any interesting Floyd's tortoise and hare, or tortoise hare? That was published 2018. All right, any interesting discussion? O(1) space solution, Mr. Pachman, 2015. This is one of the OG questions. Trigger student to check all the time whether we have reached the end of the handle in via exception. Tortoise and hare. Say why I did a speed. Look before you leap. Ah, I see. Choose, oh, what's EAFP? Easier to ask forgiveness than permission. Yeah, he doesn't post when he has nothing new to add. All right, let's try it. I never done it the other one before. The try. Let's see how fast it can go. Stephen Pachman. He is a good one. Very smart. I recommend you guys just to Google his name and see what he has achieved. Very impressive what he has achieved. So what you say is we're just gonna try. Oh, it isn't trying everything. I don't think I need to try everything. I just try this. Try everything. And then accept this, right? Yeah. Oh, I don't have to check. Yeah, I don't have to check. So we can just say, yeah, we'll just say, oh, hold on. Oh, ha. So the only thing we need to check. So yeah, I like to do this one. This while true. While true, and we still need to check this. So we can reduce one checking. We just check the other one. Yeah, so we just do one check every time. Let's see. We just say try to use Mr. Pachman's easier to ask for forgiveness. Easier, probably has a K in it. Easier to ask forgiveness than permission to improve speed. Alright, let's give it a shot. Maybe it is faster. Maybe it is not. Maybe we have to do it his way in order to make it faster. But it's all a moot point until we actually run it. So let's give it a shot. Which means we're gonna say, oh, it's 56 milliseconds. It does speed up. It does speed up. Okay. Okay, I want to do his method, the ultimate method, We're going to try n1, n2 equals head, hit on next. While n1 not equal to n2, I'm going to do this. And then I'm going to return true. Let's run it first. Make sure this one is still correct. Yeah. And we submit it again. Oh wow, 44 milliseconds. It does work. Does work. Holy moly. Holy moly, he's good. I mean, this is exactly his code. Exactly his code. This is exactly his code, and it does improve tremendously. Tremendously. So we go from 80 to 44. I'm going from 10% to 90% ranking. The reason for the improved runtime, improved runtime, is that we are doing fewer checks, fewer if checks in each iteration. Doing fewer if checks in each iteration. Wow, this is, see, this is the jam, right? You didn't know. Yeah. Impressive. Shaved off half. Runtime improved from 80 millisecond to 44 millisecond. Very impressive. All right, that's it. I mean, there's nothing more to gain out of this. 7-line code. Just reverse the list. What do you mean by just reverse the list? How do you know where the end is? Okay. Reverse head. Oh. We reverse it. Point, 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 point. How do you handle this? Well, it's leading to this, so this is gonna go back here, so it comes here. All right, it's already pointing this way, so it's pointing this way. So we reverse this way. Wait, how does that work if you want to do it in place? We point this way, and we point this way, and then go here, point, 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 and we end up. Then its reverse version must have got the same head pointer as itself. Yeah, that is correct. I think that is correct. That's a good thought. Yeah, it's actually a good thought. Huh. You know, you kind of get stuck in this tortoise and hare thing. So, all right, let's take a look at this. I forgot what this is. Return the node where the cycle begins. Ooh, okay. Return the node where the cycle begins. So we still we should not modify the linked list. So we're rotating. We know where they meet, right? That's when they meet, the first time they meet, and then we can we judge based on when they meet? And they also require to run O1, I think. Yeah, constant memory. Huh. So it's the same solution, I remember. You use the rotating thing, and then we know that once if it's not inside, right, but before it's inside, the fast node is just going around, right? It's going around and around and not doing anything. And once the slow node enters, and we don't know when it enters, but once it enters, then wherever the fast node is, then it's chasing, right? It's chasing. And then it will chase, and it will meet it, right? It will meet it. And then, right, how do we know when it enters? So the moment it enters the loop is the moment that the fast node starts chasing. And the moment that the fast node caught up on it is the amount of time, because their speed difference is 1. So the fast node, say a fast node has to make up 3 nodes in order to catch up, and then it requires 3 iterations to catch up, and that means the slow node moves up 3 iterations, and then it caught up, right? It caught up. But the question is, how do we know how many iterations it actually take? And we can start counting how many iterations it takes initially, right? And then we know that when they meet, there might be a math formula in this. So the fast node, right? So we say there are k node in here, and then there are L node inside here. Just X node and Y node would be easier. So and then the slow node can only be caught up once it's inside. So say it's inside here, it gets caught up, and the total number of iterations is m. So we have m iterations. No, I don't like that. I like m is here, n is here, and we have x iteration. In total, we have x iteration, right? X iteration. Now, what we know is the amount of nodes that the slow node goes inside the loop is x minus m, and that shall equal to, hold on, what is your n? I actually don't know what that n is. Shall equal to, so the fast node does 2x, right? Fast node does 2x, and after the fast node does 2x, what does it do? And with 2x, that's the total amount of steps that it has taken and to catch up to the slow node. So it's 2x. If we minus m, that's the amount of steps it has taken inside. No, that's not right. That's not right. It should be when it's m, the fast node took 2m, and it's already somewhere inside, right? Somewhere inside the loop. The fast take 2m. And what we want to know is just the difference between the fast node's position and the starting position. How do we know that? Do we have to also assume the size of the loop? I feel like it's just a math problem, right? It's just a math problem. So depending on when they will meet, right? Depending on when they'll meet. So when the slow node gets here, the fast node can be anywhere in the loop, right? Could be anywhere. And then as the slope moves forward, the fast node is chasing, and then it's closing down the distance one at a time. So it will catch up to it, and then we will know that once it catch up to it, we know this is the amount of steps that it takes for the fast node to actually catch up. So that's actually twice, right? Because we use the same amount of steps. So which means this shall equal to here, shall equal to this, is equal to this, and the fast node will take that amount. But we still don't know, we still have no idea about the loop, the size of the loop. Do we need to know the size of the loop? All we need to know is m, right? We know m, we know, let's say this is n. So I take n steps. So total steps is m plus n. And then we know that the fast node, when I reach here, the fast node is here. And this is also n, which means this entire thing, which is 2m, shall equal to depending how many rounds it took. 2m is a total. It could have been taken a few, and then once it reaches there, so it's going to be, let's say the loop size is L, right? Let's say the loop size is L. So it's going to be m plus, so it's going to be 2m, right? That's the total number, and then minus m, right? So m is the amount that it has taken inside the loop. So if we do m L, that's the, so it's going to be, if it divided, that will be here. If it's so it's going to be L minus this. So L minus m mod L shall equal to n. So L minus n shall equal to m to this. Which means m equals something times L plus L minus n. And we know n is x minus m. So it's going to be minus x minus m. So minus m plus m. And we see m is all gone. So we have x equals L plus k times L. What is this? That doesn't make any sense to me. Oh man, if I encounter with this one, I will be royally screwed, because I forgot. I remember it's very simple to compute. Where do we meet? I can't remember. Yeah, so they meet, right? They meet at a spot, and the spot says it goes n, and then we don't know the size of the. We probably won't need to know. Hold on, I don't think this is correct. 2m. What is 2m? No, that's not 2 1, it's 2x. All right, 2x minus m. It's 2x minus m. 2x minus, that's the total amount has done, minus m equals 2x minus m shall equal, let's say it does k rounds, and here then plus L minus M. Right, I think that is correct. This is the correct one. So if we do it this way and we substitute equals KL plus L minus M minus X. Actually, it's plus M minus X, right? N equals X minus M. So it's L minus X minus, yeah, so that's what it is. So what we have is 3x equals 2m plus k plus 1 L. We know x, we don't know m, we don't know k, and we don't know L. It gotta be in something else between L and k. L and k. L is the cycle, and k, yeah, I shall be able to do this. So 2x minus m shall equal this one. If we divide L shall equal k, right? Yeah, that's the quotient. K is the quotient. How do we even express this? Two n, take n and take 2n to catch up. I mean, I don't know. I mean, this is easy to do if you don't do O1 space. I need a hint. Let me just take a look at my solution. Yeah, kind of forgot. Huh, this is O1, detect cycle. Yeah, we have this. Oh, I wrote exactly the same code. Okay. All right. I didn't see too much. Just kind of refresh my memory on what it actually is. All right. I think what I saw is when we hit it, then we just jump out. Right? If we hit it, I say we jump out. And then what? We continue going until we meet again? Is that what it is? We continue and we continue. So we start from this position. We start from the front, right? We start from the front. Like this is the starting position, and then we keep moving, and then it will try to catch up. All right, so we have the entire, and we have this as the amount of steps the fast has to go in order to catch onto the slow. So now we can count. So when the fast caught up to the slow, I think it'll be caught up on the same time at exactly same position, same location. It's going to catch up. Does that mean we can get L? Because after each step, right after each step, it's getting closer and closer. So it will go back here. It will go back here. But we still don't know. Right? We go back here, we get L. Right? We get L. We get L, then what? If we get L, we still don't know N. And that's why we still don't know M. But we will... Are you saying that we'll always meet at the same position, at the same location? Yeah, because the fast one is ahead, is always one step ahead after each iteration, and it basically has to catch up. So it has to catch up to the small one by taking that many steps. And when taking that many steps, the slow one repeat, it goes back here. It goes back to this position. So as we go around, so we start from here. As we go around, so what will happen when the slow one get into here? The slow one get into here, the fast one, so the fast one and the slow one will be in sync, right? They will do exactly the same thing. They will do exactly the same thing. So we know the number of steps in here. So we know the loop. So we know the loop is L. Right? We know the loop, and we know. So the big one will be basically go through the loop twice. I still don't get it. How? We put slow on the head. And let them go. Oh, I remember this idea. The fast goes slow now. The fast go slow now. So this is where they meet. What he's saying is this thing equals this thing. Why? Why? I don't get it. I remember there is a very good explanation, and I cannot remember how it is being done. So I know that when they meet, that's good. They can meet at any point, right? They can meet at any point, and then we move one back, and then we let both go. And when they meet again, it says when they meet again, that will be the point that the circle starts, which means when they meet, the remaining is M. How? I think I wrote something. I can always check my notes. But I remember there is something there. Did I write something here? seen the end. Oh, yeah, that is the cheating method. I don't remember. I've done this before, man. Did it again. Alright, so I think somebody wrote a very good one. I don't know, I don't remember which one. Assume the distance from head to the start of the loop. The distance from the start of the loop to the point fast and slow meet. Yes. Distance from the point fast and slow meet to the start of the loop is yes. What is the distance fast moved? What is the distance slow moved in the relationship? Man, that's exactly what I was trying to do. I didn't read it. I just want to try to do it again. Yeah, that's what I tried to do. This is N, right? This is where they meet. And then just trying to find out the relationship between these. Point to the start of the loop. Yeah, this thing. Let's say call it P. So we know that. Well, I don't know. What is the distance fast has moved? Fast has moved n plus n plus p plus n. That's fast has moved. Slow has moved n plus n. Right? Yeah, we were talking about the total distance that they have moved. And we ignoring the thing and their relationship. What is their relationship between when fast has moved and slow has moved? Well, the relationship is 2 times slow moved equals 1 times fast moved. Exactly. The distance. No, 2 times slow moved. So are you saying that the fast only goes 1? I don't think so, man. This is saying m equals p. Right, 2m plus 2n. Yeah, this is saying m equals p. This is saying this equals this. But this is based on the fast only goes once, right? Slow goes that many steps, so fast goes this number of steps. And then we check how fast. You don't know. You do not know. It could be, I mean, fast could do n plus p. It can do any number of times, right? Because it can go multiple times inside. How do you explain that's not, that's only saying only go once? Okay. This seems to be a better one. So what we're saying is the fast has moved m plus k times m plus p plus n. This is the fastest moved. This shall equal to 2 times slow has moved. So what we get is k n plus p plus n 2m plus n. So we got m plus 2m. So it'll be k n plus p minus n equals m, right? So n plus p is this is any number, right? This is any number of time. So O can do this. K minus 1, n plus p plus n plus p equals m. So m equals p. So m equals p, and then any number of times of circles that it has done. That's a much better explanation. Yeah, that's a much better explanation. All right, I did not expect this one to cost me that much trouble, but it does because I forgot how this one is solved. All right, I think I might have done a detailed explanation in the past. All right, when did I do this? I did it last October. So let's just pull up last October. Let's see. Let's just go to, I think, 2020, 10, 27, 10, 27. Yeah. Alright, suppose it takes S steps for slow and fast to meet. S steps. Suppose there are A steps before the cycle starts. Suppose there are B steps in the cycle. And suppose slow and fast meets at kth step within the cycle. So we have S minus A. Alright, so S minus A is M times B plus K. That's true. Because S minus A, because the S minus A, it takes S steps. Because we don't know how many rounds the slow has to go around. So it can go M times B. B is the B number steps in cycle, right? So S minus A is MB plus K. 2S minus A is NB plus K. That's true. So S equals N minus MB. Now S is the steps for the slow takes for them to meet. It equals N minus MB. So equals, so the S is, I don't think this is a good explanation. So S, what I'm saying is S, which is the steps from the slow. This is it's the before and then when they meet, right? Before and when they meet. So that equals the number of time. That's a multiple of the cycle. Before we can reach the cycle start from the point where the slow and fast meet. That's B minus K. What is K? K is this, so B minus K, yes. And consider A equals this. A equals N minus 2M B minus K. We discover this means if we set a node at the meeting node and set another node at the head, and we move them both at a step time, they will eventually meet at the cycle start. I don't like this explanation. As when I'm looking at it right now, I got confused. Yeah, literally I got confused. So I'm gonna redo this. All right, suppose I'm actually gonna rewrite this. No, I don't like this explanation. Okay, I'm gonna do it later, or do it right now. Let's do it right now. Suppose there are, okay, let's just redo the whole thing. Suppose there are m steps before the start of the cycle. Suppose there are n steps inside the cycle, n steps between the start of the cycle and the point where the slow and fast nodes first meet. And suppose, let's check our notes. And suppose we have suppose the length, the size of the cycle is L. So what we have is 2 times m plus n, that's the amount that the fast has gone, equals, right, 2 times the fast has gone, equals m plus n plus KL, right? Nah, I shouldn't use L. Suppose the number of steps between where the fast and slow nodes meet and the start of the cycle is P. That is the cycle size L equals P plus N, right? So we can say K L equals M plus N plus K P plus N. So this one, what we get is we get M equals KP plus N minus N equals N plus K minus 1 times L. In other words, M, in other words, M equals N, right? That's what we get eventually. No. For K minus 1, and then plus, yeah, it's plus P. It's not, yeah, it's plus P. In other words, the number of steps from the starting node to the root node to the start of the cycle is the same as, no, I shouldn't say the same. It's same as the number of yeah, it's the same as the number of steps from where the first and the slow and fast nodes first meet to the start of the cycle. Irrespective of how many times, I didn't even define K. Suppose K is the number of times the fast node has cycled. Has cycled, yeah. Irrespective of how many times the fast node has cycled. Because it doesn't matter, because if cycled, it will stay at the same place. If done one time, if it's cycled 2 times, then n is still equal to p plus this, and that means so if it cycled once, right? If it only cycled once, then when they meet, then this is the same. If it has cycled twice and then they meet, then what we know is they're gonna so it's like they have to meet again, right? They have to meet again. So from this position until they meet again. Yeah, so hold on. Yeah, so it doesn't matter. Yeah, it doesn't matter. Start cycle the same as number of steps from where the slow and from first meet. Start cycle plus any number plus a multiple of the cycle size. This means if we place the slow node back at the root and let the slow and fast move one step at a time, both move at one step at a time, they will eventually meet at the start of the cycle. Note that the fast node might have to go through the cycle multiple times, but the final meeting place is always the start of the cycle. Alright, so we make the change to this, and hopefully this is clearer. A special case is when k equals 1, which means the fast node initially has only gotten through the cycle once. This can help us visualize the more generic situation where k is larger than 1. Okay, all right. I mean, we basically failed, but we went back and then we checked it again. So I think it's still worth it. It's very worth it. We basically went through 2 questions, right? The 2 levels of questions, and this is important. Yeah, I do remember now that I had a bit of trouble back then, but luckily I was I went to the solution. I wasn't able to do it by myself. All right, that shall be it for today. We'll see you guys tomorrow.